In this problem, I want to use the Schmidt process to find an orthogonal basis for the subspace of R4 spanned by, I know these vectors are in the glare, so let me read them to you. -1, 3, 2, 1, 5, -6, -1, -5, and 7, 4, 7, -4. So I'm going to use the Schmidt process, but I'm not going to just write down the formula and follow it, even though you're welcome to do that when you solve these problems in the homework. But I want to kind of think through it as we go here. So the goal is to build an orthogonal basis. We have a spanning from this spanning set here. So the way we do that is take this first vector, and I'm going to call these vectors x1, x2, and x3, because that aligns with the notation in the notes when I wrote through the process of developing the Schmidt process. So anyway, we'll take our first basis vector. I guess I'll keep track of my basis vectors over here. The basis vectors are going to be named v1, v2, v3. So v1 is just going to be x1. And then I'll write formulas for v2 and v3 in a second. So this is going to be our orthogonal basis. So in this case, our first basis vector is just going to be the first given vector. -1, 3, 2, 1. There we go. Okay. Now we need to come up with our second basis vector. So what we're going to do here, and this is a familiar process from a previous example video I gave, but we're going to take x2, and what I want to do is decompose that vector x2 into, let me draw a picture. So let's say here's x2. And let's say here's our first basis vector, v1, or I'm going to make it shorter this time. Let's say this is our vector v1. We want to express x2 then as the sum of a vector that's already in the span of v1. So that's already a scalar multiple of v1 plus a vector that's orthogonal to v1. And this is going to be our second basis vector, v2. So we want to take x2 and say, okay, part of this is already in the span of that first basis vector. I don't need that. That would be redundant. All I need is this component that's orthogonal to v1. So I want to pull just the orthogonal component out of x2. That's the goal. So I want to write x2 as, just copying from the diagram I drew right here, the sum of one vector that's already in the span of our first basis vector plus another vector that is orthogonal, v2, which is orthogonal to v1. In this, so in this equation, I want to solve for v2. We're going to have to find v2, we're going to have to first find the scalar multiple c. So suppose we take the inner product of both sides of this equation with v1. Take the inner product of this side with v1. So then we'll have x2 dot v1 is equal to c v1 dot v1, if I distribute this, plus v2 dot v1. And remember, by design, v1 and v2 are orthogonal. So this v1 dot v2 is 0. And so now I can solve for the scalar c by dividing both sides by v1 dot v1. So that's going to give me this scalar multiple c in this equation. And so that's going to mean that x2 can be written as c, which is this, x2 dot v1 over v1 dot v1 times v1 plus v2 plus v2. And so now, remember, what we're really after is v2. This is our second basis vector. So if we subtract this quantity from both sides, that's going to give us our second basis vector. And if you look at the Graham-Schmidt process, that's the formula it's gonna give you for finding V2. To find V2, you take your second given vector, your second spanning vector, x2, and subtract this component. So solving for V2, it's equal to x2 minus this. x2 dot V1 over V1 dot V1 times vector 1. Okay. So this is the general formula that you'll see when you look at the Graham-Schmidt process written out. In this specific case, let's see. So x2 is the vector 5, -6, -1, -5, minus x2 dot V1. Well, remember V1 just is x1. So x2 dot V1, we're taking the inner product of these two vectors. So that's going to be, actually let me write that over here. So I'm going to show the computation. So x2 dot V1 is, all right, so x2 is this vector, inner product with V1, which is this vector. So this is equal to 5 times -1 plus -6 times 3 plus -1 times 2 plus -5 times 1. So that'd be -30, right? -20, -30. Okay. So x2 dot V1 is -30 over V1 dot V1. Here's V1. So V1 dot V1 would be -1 times -1 plus 3 times 3 plus 2 times 2 plus 1 times 1. So 13, 14, 15. So this is over 15 times vector 1. So remember, what we're subtracting over here is the part of x2 that's already in the span of V1. So this is times V1, which is the vector -1, 3, 2, 1. Let me see if I can squeeze this down here. So we've got 5, -6, -1, -5. So this right here is -2, minus -2. So this is plus 2 times this vector. So this is 5 minus 2, -6 plus 6, -1 plus 4, and -5 plus 2. So our vector 2, I'm going to record it right here. This is probably too crammed together here. Vector 2, our second basis vector is 3, 0, 3, -3, isn't it? 3, 0, 3, -3. All right, there's our second basis vector. Now we just need a third one. So the way we find our third basis vector, it's going to be similar to what I showed you a second ago. So in this case, now we want to take x3 right here, and, well, let me draw a diagram again. So we want to take x3 and write it as the sum of a vector that's already in the span of V1 and V2. And so pretend like this is three-dimensional space. I know these are four-dimensional vectors, but so say V1 and V2 are vectors in R3. So then the two vectors define a plane. The span of these two vectors would be a plane. If you picture my paper as like an infinite plane, extends forever in every direction. I want to write x2 as the sum of a vector that's in, let's see, here's the plane, spanned by V1 and V2. So let's say here's V1, here's V2. It's getting a bit sloppy here, but so we want to write it as some vector that's in the plane spanned by V1 and V2, plus a vector that's orthogonal to that plane. And this guy right here is going to be our third basis vector. We need just the orthogonal component, V3. So we want to write x3 as the sum of a vector that's already in the span of V1 and V2. So that's going to be something like C1, V1. Let me write this in purple so it matches my diagram. So see something in the span of V1 and V2, so it's going to be some scalar multiple of V1 plus some scalar multiple of V2. And then we'll have this orthogonal component, V3. And what we're really after is solving for V3, but in order to do that, we have to first find C1 and C2. And I may not go through all the details of this part of the process, but what you do is you take the inner product of both sides with, let's go with V1 first. So if you take the inner product of both sides with V1, maybe I will write this out. So you'll have x3 dot V1 equals C1 times V1 dot V1, if I distribute this V1 to all three parts, plus C2 V2 dot V1. But these guys by design are orthogonal. This is already part of our orthogonal basis, so this inner product is 0, plus V3 dot V1. And again, by design, these vectors are orthogonal, so this inner product is 0. And so we can solve for C1 is going to be equal to x3 dot V1 divided by V1 dot V1. And then you could do the same thing with V2. And so what you end up with, thinking about where I want to write this formula, I guess I'll write it right here, is, well, here, let's just record it. So the C1 is equal to x3 dot V1 over V1 dot V1. That's our scalar multiple of vector 1 in this sum. If we do the same thing but with V2, you're going to find that C2 is equal to x3 dot V2, because we would take inner product of both sides with V2, over V2 dot V2. And then the other inner products would have been 0 and gone away. And so then we can find V3 by subtracting the C1 V1 and the C2 V2 from both sides. And so you end up with, thinking about, okay, I'll keep this. We end up with this vector V3 is equal to x3 minus this multiple of V1, which is this, here's your C1. So minus x3 dot V1 over V1 dot V1. That's our scalar multiple of V1. And then also take away this C2 V2. So also take away C2, which is this, x3 dot V2 over V2 dot V2 times vector 2. Okay. And so here's your formula for finding that third basis vector. All right, so I want to write this out. I'm going to have to do some of the arithmetic in my head here, but x3, which is this guy, 7, 4, 7, negative 4, minus x3 dot V1. So here's x3. x1 was equal to, we just made V1 x1, so we're taking the inner product of these two vectors. So that's going to be negative 7 plus 12, so that'd be positive 5, plus 14, so now we're up to 19, minus 4. So now we're at 15. Positive 15, I believe. We'll be able to check our answer in just a second. over v1.v1. So that was 1 plus 9, so that's 10, plus 4 plus 1, so that's 10 plus 5, so 15 here, times vector 1, which is this. Okay, x3.v2. So here's v2, here's x3. So x3.v2, I'll do some scratch work right here, is equal to 7 times 3 plus 4 times 0 plus 7 times 3 plus negative 4 times negative 3, so plus 12. So that's 42 plus 12, so 54. Okay, so 54 over v2.v2 right here. So v2.v2, well, here's v2. So again, I'll do a little scratch work over here. So v2.v2 is going to be 3 times 3 plus 0 times 0 plus 3 times 3 plus negative 3 times negative 3. So 27 times, and the numbers come out kind of nice on this. This is your first example in the notes, which is why I made the numbers kind of nice on this. So this coefficient right here is just 1. This coefficient here is 2. And so what we have is 7 minus 1 times negative 1 minus 2 times 7. So minus 14. And then 4 minus 1 times 3 minus 2 times 4. And then 7 minus 1 times 2. So 7 minus 2 minus 2 times 7. So 14. And then negative 4 minus 1 minus 2 times that, so minus 8. And so our vector 3, I'm going to write right here with the v1 and the v2. v3 seems to be, that'd be 8 minus 14, so negative 6. 1 minus 8. This would be 5 minus 14, negative 9. And then negative 13. Looks like. Let's see. So I was saying we could check our answer. This should be an orthogonal basis. So just one thing we could check is, is this an orthogonal set? So if we check this inner product, v1 and v2, we have negative 3 plus 0 plus 6. So that's 3 minus 3, 0. Great. I'm going to do v1.v3. So that'd be 6 minus 21. So that'd be negative 15. Minus 18. Oh, something's wrong.